Morty, we've got to turn the project in early.
Hey everyone, how are we doing? Good afternoon. It's about 11:25 in Knoxville. Let's go ahead and wake up Mubot right here. Who's in the chat? Who's doing work? It's time to do some homework, some quizzes, whatever you're doing. Jump on in. We'll see who's all here. Closing down previous chats. Get some Pearson up. Who's already done some of the work? It's time to do some practice. Time to do some work. See if anyone's logged in yet. I don't see any chat yet. Let's go to live chat. We're on live chat. Mubot, tell us if anyone joins in the chat. Here we are. Structure tools. Let's look right here. Mubot, anyone here yet? No one's here yet. Ah! Let's see. What does the next assignment do? Next assignment is due on the 17th. The 17th. Some people have already done it. Some people have done the homework. Not a lot on the quiz yet. So, no real attempts on the quiz. People have done the homework, though. And, yeah, it's the biggest thing is, like past due, it's going to be past due right there. Look at grades. Hey, Kaya, good to see you here. You're not in. Yeah. What would you like to talk about, Kaya? Talk about whatever you want. Talk about whatever you want. Let me know. Do some work right here. I'm looking through grades. Just chilling out for the moment. Getting grades done. Looking at assignments, and that's interesting. Yeah, the average for one of my recent 201 things was a 68, but the median was an 80. And I think that's one of the toughest things. It's where sometimes grades get really lowered by that. And then if I go and look at the confidence intervals, it's the homework. A lot of people doing the work already have been ahead of the game, and that's what I see is like a lot of times people getting it done early are the ones who are like on track. So a lot of times if you wait to the last minute, you're like, I gotta get it done, then all of a sudden the grade goes and yeah. Oh, can we talk about multiple linear regression on categorical variables? Yeah. So what do you want to talk about with that? Let's talk about that. Here we go with, let me take the timestamp here. Multiple linear regression with categorical variables. Okay, so fall 03, BAS 320, multiple linear regression with categorical variables. We're gonna maybe get to that today in my class. So let's go over here to the main screen and let's talk about that. Here we go. Okay, so multiple linear regression. What does multiple mean? Let's start here with multiple. Multiple linear regression. What does multiple mean right here? What is the idea of multiple? If I say multiple regression, what am I telling you by saying it's a multiple regression versus simple regression? What is the idea of multiple regression? More than, kind of more than two. Like if you're thinking in X and Y, yes, more than two. Multiple X's. There is what is called, it's not multivariate. It's, what is it called when you have two Y's? I don't do that analysis much. You can actually try to optimize the model on the reduction of the sums of squared on two Y's. I don't usually do those kinds of models, but I don't find them to be that valuable. I don't know. Maybe I should look into them more. What is that called again? I did in graduate school a decade ago, so I don't use it that much. So what we have right here, let's load up some data. First a library, then let's load up a data set. And here's how you make a multiple model. Multiple models are going to have in it a linear model. And we're going to say here, let's predict height based on the weight of a person and the gender of a person. Does that make sense? So that means more than one predictor, more than one X. Great work right there, Kaya. More than one X. So this is now a multiple model where this is a simple model. Simple models just mean simple, nice and easy, one X, one Y. Now we have 1y, 2x's. So the y variable of interest, y, and this is x1, and this is x2. Now, what you'll notice about this is categorical / indicator regression. So why is it indicator regression / categorical? So categorical means we're using indicators. Why is this going to be indicator regression once I add the data set here? Oops, let me bring that back. Why is it going to be categorical / indicator regression right here? And we see an important thing right there, which I'm trying to highlight. Why is this going to be categorical / indicator regression? Why is this categorical / indicator regression? So it's multiple because there's multiple x's. That's why we call it multiple. And why is it categorical / indicator regression? So categorical variables create indicators, which we'll see here in a moment. And this is categorical / indicator because gender is a what variable? If we go here and look at gender, gender is a what variable? Gender is categorical. So that's going to make it categorical because factors are categories. And that's going to make it indicators when we make our model right here. So there's the model created. And now we make a summary of the model and we take a look at the output. So going to be very important right here to understand what's going on. So I want us to try to interpret this to somebody who doesn't understand what's going on right here. This is a model trying to predict what? Let's go from the very start of this output. This is a model trying to predict what? We're doing the full output right here, which is super important. Anyone watching this, it's probably a very important thing right here to be able to understand everything on the screen, which we're going to do from start to finish, understand every bit of this output right here. This is a model trying to understand people's whats, trying to predict or explain people's whats. And for reference sake, I'm going to put the model over here in the corner. So let's go visualize model. And there's the visualization of the model. So this is a model trying to understand people's whats, their height based on their weight and gender. So we've got the model over here in the corner, getting everything all nice and pretty. There we go. And there's everything on the screen at one time. So we have a model right here trying to predict people's height, that is the y variable of interest, based on their weight, one of the x variables, and their gender, the other x variable. The data comes from survey 10, and we are using a linear model to do it, i.e. you see the lines. What do the residuals mean? Now, you want your average residual to be about 0, which means things are close to the line. But what does this residual of 9 mean, which is probably one of these people over here? What does that residual of 9 mean? Actually, it might be this person right there. It's 72. It's maybe, there might be someone even higher. It's probably that person maybe-ish. What does the residual of 9 mean? So that's the max residual from this model, which might be about that person right there, which would be predicted from the black line. The residual of 9 means somebody is what? There is an individual. The highest residual is somebody, which might be this black point right here. That is the highest residual. Somebody is 9 points or 9 values, 9 inches above what they were predicted to be. Like this person was predicted to be, they're not the residual of 9. It must be someone even higher. Sometimes the plot doesn't show you the very highest points. I don't like that about it. Code Petri created right here, but doesn't show you some things that are a little bit off the graphic. So there is somebody who is 9 above their predicted value. The minimum residual of -15 means there's somebody who's 15 below. So there has to be a data point that's 15 below their predicted value. Those are the misses the model makes. So these are probably the people who are the extremes away from their predictions. So the max and the min of the residuals. The average residuals should be about 0, and we're looking at the median right here due to skew. And then these should be about symmetric because the residuals should follow a general normal pattern. You can do this via the check regression to look at the residuals more closely. So probably rather than doing a full examination right here of the residuals, I would highly suggest looking at your check regression output. We could look at that next, but this is just a short capsulized view of what we're looking at. Next, we get to the actual regression model. Do you know how to write the regression equation from this? Because the first thing we see here are estimates. So Kaya, can you write the regression equation from this output right here? From this output, could you write the regression equation? There's a really easy way to remember how to write the regression equation. So now we're on to this output right here with the coefficients. and we need to first be able to write our regression equation. Could you do that with this output? Could you sit down right now and just write the equation like, okay, here we go. And I'll show you the quick way of doing it to write the regression equation each time. Could you write the regression equation right now? Just be like, oh yeah, that's just this. Awesome work, Kaya. Let's throw you some points. So the regression equation, once you know how to write it, it's pretty easy, and I'll show you how. And great job, Kaya. Is you go this plus this times this plus this times this. Now that looks a little bit weird, but we'll talk about it here in a second. There's the regression equation. That's someone's predicted height. You just take the first, the estimate of the coefficient. The intercept doesn't have an x variable with it. You go this plus this times this plus this times this. You just times the estimate by the coefficient, which you see right here. Usually we put the x variable name afterwards, but if you put it first, it doesn't matter. It doesn't really matter. So that's how you write it. It's always intercept plus this times this plus this times this plus this times this plus this times this. Nice and easy to do, and I'm going to write it one more time if people are seeing how to do it right here. 2 seconds. If people are wondering how to do it, you just take right here, and you go intercept plus this times this plus this times this, and if there's more, you just keep doing the process. Yeah, I like to copy paste it, nice and easy. And there it is right there. It's not going to solve, but if you put in values for this, like I weigh 200. Yeah, I weigh about 200, whatever. Maybe I weigh like 190. And I'm gender male. My predicted height is 6 feet tall. My residual is 3, because I'm 3 above that. So that is Brian's predicted height right here from this model. So now we get to the last little bits of the output, the standard error. The standard errors are your what's in your coefficients. The standard errors are your what's in the coefficient. I think of a U word, and you might not know it because if you're in another section. The standard errors I think of as my uncertainty. So if I tell you the intercept is 60.3, that's my best guess of it, i.e. my estimate of the intercept. I say the intercept's probably about 60.3. But, I could be off by about 0.5. Now, that's not saying I am off by that amount. Like, if I say I'll be to your house at 2, but I could be off by 5 minutes, it doesn't mean I could be off by 6, 7, who knows? But that's my kind of uncertainty estimate. It's almost to say the standard error is an estimate of our uncertainty. It's not to say how off we are, but maybe off by about this much. I don't know. So here's our best estimate of what the intercept is, and we could be off by about this much, maybe more, maybe less. Here is our estimate of gender male's coefficient, and we could be off by about this much. Does that make sense? What standard errors are? They are the uncertainty in the estimate. So it's a measure of variation. So the t statistic, the t value, the t statistic, also known as a t ratio, is found how? So the t ratio, sometimes called a t ratio, is found by doing this. The t ratio is the estimate divided by the standard error. So you want your uncertainties to be very what right here? Relative to your estimates, because you want large t ratios, and it doesn't matter if they're positive or negative, because that just indicates the sign of the coefficient. You want your standard errors, which are your uncertainties, to be very what? You'd like your standard errors to be very what? You want small standard errors, right? Because that's your measure of uncertainty. You don't want uncertainty. More uncertainty leads to more confusion. Variance inflation factor will come into play in that if you know about variance inflation factor with increased to variance, which is standard deviation squared, which is basically variance or standard error squared. So when you think about the small uncertainty or better estimates of coefficients, better estimates have lower uncertainty and would make better models. So if we have a high t ratio, higher t values lead to what are p values. So a higher t statistic would lead to a what are p value. And the way this looks is if you go back to 201, the smallest theoretical t value is going to be a t of 0, which would have a p-value of this. Lower p-values, exactly. So you see how it says absolute value of t right here? The sign of the t doesn't matter because when we do the graphic, we'll go wherever the t was at and do the absolute value on the other side and graph the outside if we find it mechanically. So the higher the absolute value of it, like the more extreme it is, then the more significant it is because the sign really doesn't matter. It's just the further away it is from 0. So we want a very large t value. Sign doesn't matter. I mean, it does matter when interpreting a coefficient, but p-values do go lower. That's the lowest jump show or R shows. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Maybe another one. But there are p-values lower than that. Oh, it's not 2, 2. I think it does show a second 2 if you do it. But that is the p-value right there. Ridiculously tiny, tiny, tiny. P-values do go lower. It's just carrying digits beyond that. I bet you options digits equal 20. There you go. There's the p-values. Yeah. So the p, oh wait, it's doing the 2s. It does the 2s. Look at, and the code's got all weird. That just means super duper significant. It means it's basically 0. And I wonder if there might be ways to get, let me see really quick. Package in R for really small numbers is a little aside. Dealing with very small numbers in R. There's a way to deal with very, very tiny numbers. Yeah, it's a little bit of a sidetrack. They're just basically, you could always say basically 0 for those. That's a good way to describe them. Be careful messing with your digits because you'll get weird output like that you don't want to see. That looks ridiculous. But those just mean basically 0. For all intents and purposes, they're basically 0, so they're ridiculously significant. Do we really care about the intercept being significant? The intercept means being significant means that the intercept's probably not 0. Like we have good reason to believe the intercept is not 0. Do we really care about that? That the coefficient of the intercept is probably not 0? Do we have good reason to care about that? That the coefficient of the intercept's probably not 0? Especially in the multiple world, we really don't care about the intercept. The intercept is when all the x's are equal to 0. More on what that means here, but that's if all the x's are equal to 0, there's good reason to believe equal to 0. Not super important. Now, here's where we get to the important stuff. Weight is significant in the multiple world. And then it's just significant when writing the equation a lot of times, exactly. And weight being significant in the multiple world means what? It's very important that the variable weight brings what to predicting height in the multiple world. In the multiple world, which is very important to say, weight brings with it what information? 3-letter word, TV show, something girl. These are the hints. Weight brings it with it what information? Weight brings with it what information? That the other x's are not accounting for. What kind of information does it bring? If it's significant in the multiple world, which it is, that means it brings with it 3-letter word starts with an N, new information, boom, right there, new girl was the hint. So it brings with it new information not accounted for by the other x's. There can be multicollinearity. We can look into that here in a moment. New, exactly. So it brings with it new information not accounted for by the other x's, and so does gender male. Gender male also brings with it new information. Now you might say, well, wait a minute, why don't we see gender female? That's because in indicator regression, there is the indicator variable, and then there's the what level. Do you know the name of this, Kaya, right here? There's the indicator variables or indicator variables if there's more, but there's always the what level. Starts with an R. And if you don't know, just say no idea or anything like that. But there's always the what level that we compare things to. Hence, it's something we refer to, the reference level. So the reference level is what we compare to. So let's do some interpretations right here of weight first. two individuals that are otherwise identical. So that means you have one male and another male, but they differ in their weight by 0.03, excuse me, but they differ in their weight by 1 pound, are expected to differ in their height by 0.03 inches, because they're otherwise identical, but they differ in their weight by 1 pound. But two individuals who are otherwise identical, and one is male and the other is female, they are expected to differ in their height by what? Good to see you, Meet. This is the next chapter we'll get into probably at the end of today. Two individuals who differ in their, two individuals who are otherwise identical, but one is male and one is female, are expected to differ in their height by what? Look at this right here. Do you see this? This is about at 64, and that's about at 69 right there. Exactly. Two individuals where one is male and one is female, but they're otherwise identical. Like, they have the same weight. Like, these two people, would you agree with me? If I take from this model right here, visually speaking, and both of these people, person A and person B, what can you tell me is the same about both these people? Person A and person B. What is the same about those people? Tried to draw it as best I could. I'm going to put them right here so you can see it. Person A and person B, what can you tell me is the same? Good to see you, Blake. Oh, no, we started a little bit early. What can you tell me is the same about those people? Person A and person B, which are located right there and right there. They have the same weight. Good to see you, Shreya. So they have the same weight. Does that make sense? They're the same weight, but one is male and one is female. So they have the same weight, but one is male and one is female. And you would expect them to differ. So they're otherwise identical, right? Two people who are otherwise identical, but one is male and one is female. The expected difference in their height is 5 inches. Maybe because guys are usually what? I mean, it doesn't mean always. Doesn't mean always. Guys are usually what? Like, you take a random guy, you take a random girl, and what? Now, they should be otherwise identical, quote unquote. But you might say, well, guys are probably about this compared to girls. They're usually taller, right? And maybe about the average guy is about 5 inches taller than the average girl, right? So you'd say, well, man, guys are about 5 inches taller on average. So that's what we're looking at right there, is the expected difference between two people who are otherwise identical, or one is a guy and one is a girl, the expected difference. So that is how we interpret it. So the interpretation is two people, because this is people we're talking about, who are otherwise identical, which means they're the same weight in this scenario, where one is, then we say the indicator level, one is male, and we say reference level, one is female. The expected difference between their height is 5.025 inches, where the male is expected to be taller. Does that make sense, Kaya? Listen to the components again just to check. We have two people, because that's the context of this, is people we're talking about here, who are otherwise identical, because we're in the multiple world, where one is male, indicator level, and one is female, reference level, are expected to differ by 5.025, which is the coefficient. We always say otherwise identical when interpreting multiple world, otherwise identical. In the multiple world, always otherwise identical. So if you have multiple x's, you have to say otherwise identical. In the multiple world, you say otherwise identical. And then with categorical, you have to compare indicator to reference. What would be indicator and reference when there are more than two levels? Great question right there. So let's try that, and we can do that very easily by doing the following and change this to handedness. So now take a look. Here's the model. And there it is right here. And look at the coefficients. So two people. Well, so where is the reference level now, and what is the reference level? Now, it's nice on how it does it visually. So what is the reference level, Meet? And you can kind of get a hint on, oh, no, not ambidextrous, definitely not. You can see what the reference level is because it's the one that doesn't have a coefficient. Technically, the reference level would have a coefficient of 0 if it had one, but everything is compared to it. So what is the reference level right here that everything will be compared to? So this goes to Meet's question right here. Really good question. What is the reference level currently for this new model? What is the reference level for this model? And then Kai might know also. So the reference level for this model is what? Look what you don't see. Ambidextrous is the reference level. The reference level is always the what alphabetically. Great note to have right here. So Kaya's seeing it right there. It's alphabetical. Female comes before male. Female's the reference level. Ambidextrous comes before left and right. It's ambidextrous. It's just the way the algorithm runs. You can technically make one the reference level, but by default, it's the first alphabetical. Now, you notice the reference level does not get a coefficient because everything is compared to the reference level. So who is expected to be the tallest? Who is expected to be the tallest right here? So does that make sense, Meet? There's 3 levels, so there's two indicators. There's always one reference level, and then the other ones become indicators to indicate the difference from the reference. And those differences are small. So who would be expected to be the tallest right here? Who would be expected to be the tallest out of all these people? Handedness left, exactly. So the level is left-handed, and the handedness is the name of the variable. So this is an indicator variable created from the handedness variable. Handedness, the variable, creates the indicator variables, handedness left, handedness right, with a reference level, handedness ambidextrous, which we compare. So people who are, and let me ask this though, you ready? Who are expected to be the second tallest from this? Who are the second tallest people? And it's very hard to see graphically, but I'll show you. So left-handed people are expected to be the tallest. Who are expected, and these are good, tricky test questions, who are expected to be the second tallest from this model? Now, the differences are not significant. I'll show that in a moment too, but who are expected to be the second tallest from this model? And you can see it in the model if you view it. Good way to view your model a lot of times. I know, right, Trey? These are really good. Like, you can view it. So who's expected to be the second tallest? Who would be expected to be the second tallest? You are correct. But Meet, we don't see good answers. Ambidextrous is very hard to see. Ambidextrous is that black line right there. Do you see the black line in the middle of the two? Because right-handed is above ambidextrous. Excuse me, left-handed is above. Left-handed is the red line, which is above ambidextrous. Right-handed is below ambidextrous, and ambidextrous is in the middle because you compare. So right-handed people are expected to have a height that is lower than ambidextrous. So ambidextrous is between them. Ambidextrous has a coefficient of 0 technically. That's why it's not displayed in the output. It doesn't get an indicator variable. So, but they're still considered in the model. It's just that the other lines are compared to them. And so does that make sense, Meet? So you don't see it. Reference levels, the hidden gem, exactly. Great answers. And Shreya, good to see her and good practice. With the reference levels, with indicator variables, this is the new thing. This is a whole chapter, Meet. And so once you understand it, it's like, okay, we're just doing categorical variables right here. And so here's the issue though. Now that there are 2 levels to ambidextrous, how do we need to look at the significance of the indicator variable? What would we need to do to look at the significance of this indicator variable? What do we need to do? Because we should remove the variable as a whole to look at the significance of it, to say, let's look at a model with this and without this. How would we look at the significance of that? To say, let's take it completely out of the model, compare a smaller model to a larger model. Close. So these are the significant differences from the reference line to see if adding in these indicators, and you got it right there, Meet. Yep. This is like, does adding the indicator bring new information, which is the difference from the reference line? That is not really what we want to look at. We want to look at, does adding the variable as a whole help out? So we want to make a model. And here's the thing. You ready? So this is, let's call this, watch this work. Okay, so this is complex. And this is simple. Oops, should have just done the paste. The simple model has less variables in it than the complex. And we go ANOVA, simple, comma, complex. And there's the p-value right there. Or there's the p-value right there. Or there's the p-value right there. You don't have to do the partial F now. What do you think drop 1 tries to do? Drop 1 looks at what for you? What does the code drop 1 do? Think about drop 1. It drops 1 what from your model? Oh, thank you, Kyrat. There. Well, that's the goal, is to be like, okay, so what do these codes do? What does drop one do? It drops one of the variables. Thank you, Blake. It feels so nice. Drop one drops one of the variables. Weight is statistically significant. It brings with it new information. When you drop handedness from the model, how many coefficients are being dropped from the model? So let's take a look at the summary. Sure, that's there. And then when you drop handedness from the model, how many things are being dropped from the model? When you drop handedness from the model, how many coefficients are leaving the model? When you drop handedness out of the model, how many coefficients estimates are leaving the model? 2. So that's why you see this right here for 2. This is the reduction in sums of squares, which is very small. Remember, we're trying to reduce the error for the sums of squares reduction, which increases the R squared, which is amount of variation explained. So this is a very small reduction thanks to it. And the small reduction is not statistically significant. The F ratio is the ratio of the observed over the expected. The main things to see right here is probably the 2, and the biggest thing is the p-value to tell us that handedness does not bring with it new information. Huge hints for the take-home. This can also be called a what's test. Looking at the impact of one variable is the what of that variable in the model, and this test right here to remove a variable as a whole is known as the what of that variable test. Think of why it's called this also, like you're looking at the what of that variable. And so the drop one is actually doing a this on each variable. What is it called to look at the impact of a variable on the model and to say, does it have an important this on it? What is that called in statistics? Turn a what on it? What is the name to look at? What is the name of the impact of a variable as a whole, to say, let's look at the impact of this variable. Let's look at the what it has on the model. What kind of test is that? To say the impact of a variable as a whole. The effect, right? An effects test. What is the effect of this variable? And look, the effects test, does that make sense? It has the same p-value. So the drop one is running an effects test on each variable. It's called an effects test, like in effects. What's the effect of this variable? Like, is this, I guess, effective? Is it effective? I guess we could call it that. It might be effectiveness as far as I know, but I call it the effects test or an effects test. Like, what is the effect of this variable when added to the model? And it's running it right here for you. The visualized model, which Dr. Pichu created, is running the effects test on the categorical by removing it and actually doing the drop one. I'm just showing how things converge to the same answer to tell us handedness is what. Everything we're learning right here tells us handedness is what. What are we learning repeatedly about handedness? Repeatedly with handedness, we are seeing what here in this output. Whether the drop one, which runs the partial F on each one, whether we have this right here, this guy, we are learning handedness is what? It's not significant. It does not add new information. Perfect answer right here. But check this out. If we go back to gender, notice how gender has a much larger gap. And watch this. What do you notice? I wish it was smaller p-values to be easier to see. What do you notice about the p-values for the drop one code of gender and the p-value here? What do you notice about the p-values right there? The p-value right here and the p-value right here. Now, they are carried to the extreme decimals, but what do you notice? Nice job, Wes, right there. Yep, great job, Wes. Wes, keep up the great work. Wes, I swear I want to say to people, like, when I look at hours of people who attend, and I might run the analysis, people who attend, like, and watch live, the grades are higher. Like, I can't promise people that you'll do well if you watch, attend, and do the work, but there's a trend in the data that shows you come to class, you do the work, your grades are higher. But it might be correlation is not causation, because maybe people who come to class just study more outside of class. So I'd like to think I play a role in it. But hey, Shaq, good to see you here. You know what's really interesting? This is a thing you don't need to know. Can anyone do 18.253 squared in their head? You gotta think really hard. I think we have it. Terry's been talking about the project. He might be releasing it later today, I hope. 18.253 squared is about 333, I think. I think it's about 333. Oh, look at that. It's about 333. Aw. How'd I do that? A very fun fact is that the t squared is your f statistic. A very just fun random fact. Fun random fact. You don't, definitely not on the test, but I don't know. Sometimes I just read too much stat stuff. Oh, thank you so much. Wes. You're cracking me up, Wes. Well, we want to make it fun right here. Talk about some video games and stuff like that. People who attend office hours are likely, yeah. And whatever you want to work on. I think we've covered a lot of this output right here. The residual standard error is what? So we only got a little bit more to cover. And please let me know, next topic, whatever people want to cover, just let me know. What is the residual standard error, 320 or 201, if you know what residual standard error is? Typical miss the model makes. I got a Nespresso machine, $4 on Facebook. Ooh, that's a good deal right there. Nespresso, some good stuff. The typical miss the model makes. You don't need to know degrees of freedom. That's used to calculate for the F distribution. Here's the two things for the F. It's just used to calculate p-value. Degrees of freedom, not super important, just used for calculation stuff in the background. I mean, important for calculations, but not important for business analytics interpretations. The next thing to know is the R squared. What is the R squared? Very important for 201. So what is R squared? What is R squared? Should know it like this by now. People are probably typing it out. 201 should know R squared also. R squared is a super important concept which deals with the reduction in sums of squared error, variation being explained, but it deals with from the naive model, from how much variation there was to begin with, from the calculation of the mean of the y. Just throwing some things out there, but we're trying to explain height, right? Good question, Kai. We'll do that one next. Blank percent of the variation y is explained by the variation x, or in this case, the x's, multiple x's, which, or you could say the model, which is the x's. So the difference between the multiple r squared, which has a straight interpretation, and the adjusted r squared is adjusted r squared. A great job when looking at correlation. Exactly. We would have to check the direction in the simple world. Good answers, Blake, right there. I'll some points for that. So the adjusted r squared, what happens to r squared as we add in more variables? And great job right there, Kaya. What happens to r squared as you add in more x's? What happens to r squared? If you add in more x's, what happens to r squared? R squared will always do what? It gets larger. R squared goes up. So you notice right here, I have a ridiculous model with all two-way interactions, and r squared goes up. Here's a ridiculous model with all three-way interactions, and hopefully we don't just break r. Might not even be able to do this. Probably have some zeroed out coefficients. So here we go. Oh my gosh, and look what we got, an r squared of 1. We did it! Woo! Look at my model has no error. It's got, it can't calculate error, not a number. That stands for not a number. Do you think this is how we do statistics? Does this sound like a good idea right here? Look at this. This is the most beautiful model ever. Beautiful model. Do you think this is a good way? Not a number. All those, not a number, not a number, not a number. It's what NaN stands. Oh, there's some coefficients. Do you think this is how we do statistics? Good statistics? It's the output's so much it even went off the screen here. Does this sound like good ideas? No. 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 Ooh, Shreya right there, 1,000 points. Very overfit. Shreya's like, you better go make a training and holdout data set. More on that in 474 on training and holdout. This is a horrible idea. Why does, not a numbers all the way through. So why does r squared adjusted exist? Why does r squared adjusted exist? And I'll draw it out this way. I think a drawing can really help. Why does r squared adjusted exist? Why do we have it? Good to see you here, Moira. So we're talking about r squared versus r squared adjusted. So here is your r squared. And just like with decision trees, r squared, when you add x's, if you go from 0 x's to like 100, r squared is going to go what? And Meet's good answers right there. R squared is always going to go what? R squared will always go up. Does that make sense? R squared will always go up. But r squared adjusted R squared adjusted can go down. Great job on ultimate Blake level. I love Blake right there at the ultimate Blake level. R squared adjusted can go down. I know. We tried it. We only got 3.5 more weeks left, so we're trying to get people up there to the points to get to the max level. That's kind of my goal. Thank you to everyone who's been here. Wes has been here for 43 hours. Definitely earned it. We throw out some big points, but I'm aiming for 95 hours. Nice. Thank you to Moira and everyone. Seeing a lot of people with the high hours doing really well. So show up, #work. That's what we do. Shreya right there, getting tons of points at the mid. We got Shreya at magnificent Moira level, and we got ultimate Blake level. I love it. So good stuff right there. Love it. Okay, so what concepts do we see about R squared adjusted right here? R squared adjusted what? R squared adjusted what? Tell me some concepts for R squared adjusted that you should know for your test. R squared adjusted what? It can go negative. R squared adjusted can go negative. Because an R squared adjusted will always be what to R squared? R squared adjusted would always be what to R squared? R squared adjusted, because it's adjusted for how many variables are in the model. So R squared adjusted is when you take R squared and subtract a penalty. Now, the way the penalty is calculated is based typically, in large sense, on how many x's are in the model. There is more to the calculation than just that, but a big portion of the way it's calculated is based on the x's. So models with more x's receive higher penalties, generally speaking. There is the caveat that if they do much better, they'll receive a less penalty. But generally speaking, models with more x's receive higher penalties. So it's adjusted for how many variables are in the model, right? So it's a fair way to look at it, because models with more x's will always have what's. Like if you have the same x's and then have more x's means always more what? More x's means always higher what? Like if you have the same x's and then add more in, you will see this. If you have the same x's and then you just put more x's in, this will happen. There is that. There could be uncertainty due to variance inflation factor. The R squared is going to go up. Does that make sense? R squared will increase. But now, and there could be redundancy. That's good answers right there. There could be that. So R squared will go up if you add x's, right? But R squared adjusted could what? Like Evan right there. R squared adjusted could go what? R squared adjusted could go what? And if you want to do a new topic, just let me know, because we're kind of rounding out the output here on this. R squared adjusted could go what? R squared adjusted doesn't have to go up. Oh, we're talking about 320 R squared and R squared adjusted currently. R squared adjusted is just R squared adjusted for how many variables are in the model. So R squared adjusted could go down. So if you want to know if your model is good, you can look at your R squared and R squared adjusted, and they should be kind of what to each other. This is good. Your R squared and your R squared adjusted should be kind of what to each other. Your R squared and your R squared adjusted should be kind of what to each other. Your R squared and your R squared adjusted should be kind of similar. So everyone, I think some faces right there. That is this is just ridiculous. This is bad. Like this is like, uh-oh. Like your R squared and your R squared adjusted are very far apart. I mean, this is kind of meh. That's all right. That's all right. You want them to be kind of similar. So you look at your output right here and you say, well, we can't even get an R squared adjusted right there. This is actually not that bad of a model. We get a little training over for it. I don't know. Here's the R squared adjusted. Here's the R squared. And it's about 98% of our original R squared. So not a horrible model. It's got a lot of variables in it. Very, very large model. A lot of the X's are not significant. So they're not bringing with them new information. We're trying to predict someone's height. And we could use this model to make predictions. And what does this mean right here? When I predict someone's height using this model, I'm what? When I predict someone's height, oh, we'll do insurance company, yeah. When I predict someone's height, I'm usually what? When I predict someone's height, I'm usually what? And then we just have one last bit to cover in this model. When I predict someone's height using this model right here, this ridiculous model, oh, definitely, we'll do it here next. I'm usually off by about that. That doesn't mean I am off by that. Doesn't mean I will miss by that. It's like, I'm usually off by about this. Like if I say to you, dinner will cost $50, but it could be off by about $10. Would you freak out if it was $61? So let me say this statement again. Dinner will cost, I estimate dinner will cost $50 for an awesome steak. I could be off by about $10. Would you freak out if it costs $61? Would you freak out? No, don't do that. Would you freak out? What would you say to me? You'd say, well, yeah, it's about $10. Does that make sense? You'd be like, oh, it's about $10. Would you freak out if it cost $55? Well, I estimated 50, right? So that's kind of close to the estimate, right? Would you freak out if I said dinner costs $50? I could be off by $1. Now would you freak out? I say dinner will cost $50. I could be off by about $1. Would you freak out at 55 now? Would you be like, hey, you said 50 and you could be off by about $1? What's the T statistic on this? This was the estimate. This is the actual. This is the uncertainty. What's the T statistic? Just observed minus expected over standard deviation. So what's the T statistic? Here, same math, but without using 1. Same math. What's the T statistic? Observed minus expected over variance. This is the variation about how much I could be off. So you observe the dinner costing this. You expect it to cost this. This is the standard deviation. Five. Is a T statistic of 5 very large? Now, T's and Z's are virtually identical for those who don't know what a T is. Is a T statistic of 5 very large when you think about the standard normal? Probably the worst normal I've driven in a while. Drawn, driven. Is a T of 5 very large? Because we are over here. Oh, it's ridiculous. It's ridiculous. So if the dinner is $60 and I tell you it should be about 50 for a Z-score, and T's and Z's are very similar in how we use them. More on those coming up for 201 start of next week. No, next class, literally next class is T statistics. T's are basically Z's. More on that coming up soon. But this would be super unusual to be like, you said it was 50, but you could be off by about $2. It was 60. That's super duper unusual. So when we look at this right here, the same thing works for the standard error right here, the residual standard error. The typical residual is about 2.645 away. That doesn't mean that all residuals will be that. It means generally we expect them to be that far away. So that's the certainty in the residuals to tell us that when we make misses, we usually expect the model to miss about 2.6. So you see some are bigger, some are smaller, and that's a totally different model. But the residuals are how far they are away from their lines. So let's do some 201. Good stuff right here. Thank you, Blake and everyone. That's a little bit of the advanced stuff right there. Blake's got an insurance company, checks police records. Oh, this is the teenagers driving, right? Is this the proportions of teenagers who are in an accident? I think, right? Okay. Proportion of teenagers in an accident. Quiz time. Playing a Scrabble game with my mom. We're 2 and 2. She reads way more than me. Tough competition. Need to play her in Pokemon Go and battle. Got 6 years of playing Pokemon Go. Oh, don't confuse him even more. Insurance company, where's it at? Yeah, we're playing over the phone. I get confused all the time. Probably. Am I confused? Probably. Chapter 13. Yeah, thank you, Moira, right there. I think it's pretty straightforward. It's pretty straightforward on, can we play Scrabble? Let's play like a last Scrabble or something. If you understand the, I'm trying to find the question. Here it is, found it. Okay. It's all about those equations. It's all about those equations. Wow, it took me a minute to find it. Here we go. Let's do it. Okay. Yeah, Shreya. Cat's so shiny. We're getting close to best friends in Pokemon Go. Good work. Good work. Crazy eight match on a game. So this is a very limited question. And what's really amazing, 91,574. 91,574. 91,574. There's kind of the answer to it for the confidence interval. So a lot of times in business analytics, the biggest thing is interpretation, which a lot of this focuses on. Knowing the notation, you can solve things like that. So let's find out our notation to begin with and solve this by hand, which is probably the least fun way to solve it. It's much more fun to be like, hey, let's just solve it using programs to solve it. And you just put in the values and it solves it for you. So let's get the notation for it. What is the notation from this problem? Who can help me out here? We need to know the notation to solve this. So it says an insurance company checks police records of 574 accidents. That's the amount of accidents they're checking. And notes that teenagers were behind the wheel in 91 of them. So that's all the notation we need to solve this. It's like, that's very limited. It also wants a 95% confidence interval. We do need that. So 95% confidence interval. So what is the notation? I'll give you hints. We need something for that, something for this, and something for this. What do we got? Sample size. Good job right there on the sample size. That is the N, which is how many observations we are looking at. So that is the sample size right there. What else do we have? Write down all, if you are watching this right now in the future, write down N, sample size, how many observations we have, half the notation. Evan right there is also showing P hat. So Evan has calculated P hat, which is 91 over 574. And that is going to equal P hat. What is the formula for P hat, Evan? Which will also tell us what that other bit of notation is. What is the formula for P hat? Like, you've written the formula. Great job right there. What is the formula for P hat? Because it's the sample proportion. It's X over N, which tells us that this is X. X is number of successes. Successes sounds like, wait, that's a success. It's just the thing we're interested in seeing to say we saw 91 things we are interested in seeing. So X is number of successes. P hat is percent of successes out of total trials. So if you look right here, the amount of successes we have out of the total trials is what P hat is. Now, as soon as you find P hat, what are you going to find as soon as you find P hat? We now know P hat is equal to what? It was equal to 0.15853. What do we find right there? And Evan already has it, is Q hat. Q hat is just the complement of P hat. So to find Q hat, you do 1 minus P hat. They are complements with an E. And there's Q hat right there, 0.84. There we go. Well, it rounds, so let's put the 7 to make everything nice and purdy right there. P hat plus Q hat should equal 1 right there. And now the last thing we need to find is this. Now, let me point out where that matters, and we've got a lot of our notation marked. The formula is P hat plus or minus the Z star times square root P hat Q hat over N. You notice a lot of your notation right here, the N, the X, we don't need the color for that anymore, so let's go right here to the blue, and that is going to be this. The star tells us on the confidence right there, so the star is relative to that confidence. And the P hat is this. And there's our P hat value right here. And the Q hat we'll do in the darker green right here. Ooh. Oh, yeah, it works. That works nice and neat. And there's the Q hat right there. So there's our values. And so how do we find Z now? How do we find the Z, which is relative to the percent confidence? How do we find the Z? How do we find the Z? David M. Lane, great job right there. Good work. And it is 1.96. We got to throw you 1,000 points right there for that. That is a classic number in statistics, 1.96. Let's show how to find it. We're going to open this up in a new tab and bring it over here to the main page and show that we go to the second button to get the value from an area. We enter in 95% shaded in, and I like to show my confidence interval as the area between. So that's the middle 95% with a z-score of 1.96, which is basically 2. Now make sure to use 1.96. So we go right here, and the value of the z is equal to 1.96. And there's the value right there. Let's make the 9 look a little bit better. There we go. And so now we just plug in the values. Make sure you know that everything... What is everything from here over, Evan? Everything from there over is known as the what? This is the confidence level. This is the standard error, which we just talked about those in 320. So this is relative to the confidence level. Someone's called the critical value also, which gives us the confidence level. Everything from there over is known as the what? Everything from there over known as the margin of error. Everything after the plus or minus is the margin of error of the interval, which tells us the confidence level and also a measure of variation. The ME right there, the margin of error. So, man, so much little tiny writing. I like what Moira said, how this is a little bit easier of a chapter. It's a lot of notation. Know your notation. And so now we take right here, we do 1 minus, times that by that, divide by 574, square root. That is the standard error. So that's the standard error. I've already square rooted it. This value currently is the standard error. We're going to multiply it by 1.96 to get the margin of error. There's the margin of error. It's about 3%. Good to see you here, Amanda. And so now, so it's basically 3%. I wish it was. Nice and pretty interval. It's so close. Gosh. Go. Yeah, get ready for class. You know, got a good 30 minutes for class. And so there it is right there. It wants it as percentages, so watch out. A lot of fun. Let me go here and do the following. Let's go left, make smaller on screen, go right. There we go. And here we are. So now we can see the work right there. You want to turn this into percentages. So 15.853 plus or minus 2.988. Be very careful on the mathematics because it's very easy to just handle a decimal incorrectly. And so 15.853 plus 2.988. And it wants to 1 decimal, so that's 18.8. And then we go over here and we do the other one, 15.853 minus 2.988, and that's 12.9. Here we'll copy, paste, round up to 9, and that should be correct. And the work inside of jump or an R is very close. R uses a chi-squared distribution for it. There's the chi-squared. That's the chi symbol right there. We got 12.9, very close to that, and we got 18.8, very close to that. The chi-squared is a right skew distribution, so the values are a little bit more pushed to the right. It's just a different way to calculate it. To do it in the calculator, you could also use 1 prop z int. So use 1 prop z int with x and n. So if you want in the calculator, use 1 prop z int. That's found under stat test. What is that? Do you have a TI calculator? You can also do this in the TI calculator with 1 prop z int. So let me go find that. 1 prop z int. The phone probably doesn't have it. TI calculator. Man, I got a lot of playlists. TI tutorials, should call it calculator. 1 prop z int. I'll drop this in the playlist right here. Let me click the first one. I don't usually show this because not everyone has calculators, and I made short videos right here showing how to do all these. One prop zint right here. Very short video on how to do it. There's the one prop zint video. And I show how to use the one prop zint with the X, the N, and the confidence level. And check out that video where you enter an X, N, and confidence level, and it literally solves out the problem for you and gives you the upper and the lower and the p hat, which is the sample proportion right there. Oh, that's Brian talking. Where did I hear myself? So those are the values right there, and you can get them via the calculator or do them by hand. Can you do the environmental energy? Yeah. I'm going to take a quick break and grab something real quick and then do that. Explain what the interval means. I am 95% confident that the true proportion of teenagers involved in accidents is contained in the interval blank to blank. Please know, and I think we have these from yesterday, the interpretation as follows. The last exam really doesn't have them. This exam does. There's limited ones for the last exam. The next exam, the third exam, there's really a lot you can do with the final that TI calculators can help with. But then I've had people who use TI calculators and make like a 50 because they're like, it'll do everything for me, and then they don't know what to do. I've had people make hundreds not using it. So don't think you have to have it. It's just a help if you do, but it doesn't mean you'll ace it. I can do all the work without the calculator. It just can speed things up. It's just like I'd use it as a double check. So I am 95% confident the true proportion of accidents. No worries. We're practicing. Remember to write these out. Now, what does a 95% confidence interval mean? 95% confidence interval mean 95% of random samples will produce confidence intervals that contain the what? The sample proportion or the true proportion? Very important right here. 95% of random sample sizes of 574 can make confidence intervals that contain what? The sample proportion or the true proportion? Which will they contain? The true proportion. The sample proportion is always the center of the interval. The sample proportion is p hat, which is the center of the interval. That's inside the interval by default. We are trying to make intervals to estimate the true proportion. A political arrow says that in about what percent is 1 in every 5 accidents? 1 in every 5 is what percent? 1 in every 5 is what percent? 1 in 5 is what percent? 1 in 5 accidents is what percent? 20%, right? So do you think their claim is true? Would you believe their claim? Look at the data. The data says the true proportion of accidents that involve teenagers is probably between about 12.9 to 18.8, as in I'm 95% confident the true proportion of accidents that involve teenagers is containing the interval 12.9 to 18.8. So do you believe their claim? Do you think 20% is a true value? Yes or no? Because I'm 95% confident the truth is somewhere in this interval. That interval seems off. Can you tell me your numbers, Evan? That sounds like too wide of an interval. Tell me your X and your N. Something happened with your numbers. You might have your numbers are off. Here, I'll check your work and tell you your margin of error in a moment. I would not believe their claim. The confidence interval contradicts the assertion. The figure quoted is outside the interval. Should get 100. Yes. Okay. 99. Okay. So, and 95% confidence. Okay. 99 divided by 569. There's your p hat. There's your q hat. There's p hat times q hat divided by 569 square root. And that should be your margin of error, Evan. So 3.1, when you times this by 100, that should be your margin of error on your interval, 3.11. I'll be back here in just a moment, everyone. Back in just 1 minute. Woo, we're back. You might be able to do the history on the iPhone calculator. Let me go look at that real quick. History on the iPhone calculator. Calculator 8 plus 8 equals 6 minus 6 equals... I don't know. Maybe there isn't. I don't see it on here. It's a nice calculator, though. Looks nice. I don't see it. Got C... I don't know. I'm trying to find a... hard press. And you just copy. I don't see it. Yeah, the Google... Yeah, is it the Google calculator? Yeah, or R. Or use R, right? So another reason we love using R is we can see the history of the work we've done. Did you get that 3.11 is your margin of error, Evan? So then take and find the p hat again, and then do times 100 p hat, and then just double check your work. You should get 3.1149 when solving for the margin of error by percentage. And the environmental engineering worries that many cars, the hiccups. Always got hiccups. Environmental agency. Environmental agency, what are they doing? Set to a 1. I've been sleeping like 13 hours a night. 9 hours a night. Okay. Let's find that environmental agency question. Oh my gosh. Wait. Found it. Let's do it. Here we are with the environmental agency's question. Ooh, this is a good one. Okay, it seems tricky. Gonna be a little backworking, some algebra here. We love some algebra. An environmental agency worries that many cars may be violating clean emission air standards. The agency hopes to check a sample of vehicles in order to estimate the percentage of margin error of 4% and 99% confidence. To gauge the size of the sample, the agency first picks 40 cars and finds 4 with faulty emissions. Okay. So, 1,000 points every bit of notation in here. Name every bit of notation. This is a tough question. Every bit of notation you can name. Start. Go. I'll highlight them. You tell me what they are. N equals 40. ME equals 4%. Like, and 1. Confidence interval. And so what z-score will that be? That is correct. The z-score for this, we need to go and find 2.5758. Yep, that's right. Let's show how to find it. We go in. Great job. And great job, Moira, right there. Yep. This is a really tough problem. The z-score for this on the David M. Lane, make sure to be on the second button right here. Make sure to click between, and it's 2.576 or 58 if you know the extra decimal. There it is right there, 2.576. So we have to go that far out on the curve. And then this right here is X. Well, the first kind of a run trial of it. And this is going to be used to estimate P hat is equal to X, basically, of our original test over N. And here we are right here. And there it is. There is P hat. So what do we get now? I think, and be careful, technically, and Evan, I think you see it, Q hat technically is this. So there it is right there. Now, what we're trying to solve for is we're trying to solve for a margin of error of 4%. So what we want is margin of error is equal to, I'll write out the full thing first. So P hat plus or minus Z star P hat Q hat over N square root. The margin of error is just everything after the plus or minus. So we want margin of error to be equal to 4%. But we want to know what sample size will have us do that. Now, this is just a way to estimate from the first part what P hat is to give us an estimate. So we're going to do the following here, and this is going to seem a little bit crazy, but watch the steps. We're going to take and solve for this. Does that make sense? I'm going to solve for N just mathematically because I already have P hat, Q hat. Now this is a different n right here. This was used just for estimates. We want this n to solve out for where margin of error is 4%. How is everyone doing on this right now? This x and this n are just used to estimate what p hat and q hat are. If you don't have them, which another problem does, you have to estimate about 50-50 because you don't know. So they're just giving you an estimate of what p hat and q hat are based on some trial studies. How are people doing on that? This is not the n we're looking for. We want to know an n that gives us a margin of error of 4%. This was just used to create an estimate of what p hat is. How are people doing on that? We don't know the sample size we need yet. We're just saying, okay, that makes sense. Good stuff right there. This is a very tough conceptual problem. So now what I'm going to do right here is I'm going to go through and I'm going to solve the problem to solve for n. So what I would do first is I would take margin of error, divide by z, and then I would say this is equal to square root p hat q hat. What would be your next step to kind of get everything to solve for n? What are you going to do next? Good to see your Chase. What would you do next mathematically or algebraically to this to kind of get to that z? You want to start unpacking this and get towards that n right there. So you want to solve for n, so square it. Boom, Moira, you got this. So me over z quantity squared is equal to p hat q hat over n. Now, one of my favorite tricks is you can just flip things. If you just mathematically flip things, you can just go right here and say z equals me squared n over p hat q hat. And then just do what? So you can just flip things. Mathematically, it's the same if you flip them. So now what would you do next? What would you do next? Because now we're just one step away from being able to write this out and then just solve for n by plugging in numbers. Because remember, we're just trying to solve, we're just writing this in a way that we can just plug numbers in and solve for n. Multiply by p hat q hat, yep. And so now p hat q hat e times z over me squared equals n. There we go. That's it. So let's check this out. So now we just need to plug in values. P hat and q hat are, I'll write in green, are 0.1 times 0.9. Then the z-score was 2.578 over the me. The me is 0.04. It needs to be as a decimal. That should do it right there. I think this one's similar. Yeah, we'll check that one out next. Very similar problems to it. This is a big algebra problem right here. Oh, we need to square this. Don't forget to square this. So we're just taking and plugging in values, and this will solve out to n. Like this is the quantity n. Like this whole thing is the quantity n when we solve it. So first, solve everything with the radical right here, with the square. 2.578 divided by this. Square that, so multiply it by itself, times 0.9 times 0.1, and then round up 374. Make sure to be very careful in your work on how you solve this. You first do 2.578 divided by 0.04, square it, times by 0.9, times by 0.1, which you could just times by 0.09. 374. Tough problem, very algebra related. And that should do it. Yay! Good, tough algebra problem right there. So the number one way to solve this is all about that notation. Definitely, like if you know the equation here at the end that I wrote down, you can just plug in the values like that. If you know what your p hat, your q hat, your z, your me are, yep. It's a good question. It's really good for notation review. And the other one is editors reporting. This might be our last one for the day. Editors report preparing. Editors preparing. Editors preparing. It's very similar. So this one is pretty much the exact same problem, but it doesn't give you p hat and q hat. So if you don't have p hat and q hat, and I know this sounds crazy, but what would you assume about p hat and q hat? If you do not have p hat and q hat, and this sounds crazy, what would you assume about p hat and q hat? If you don't have those values, what would you assume? I'll try to do one more. This one won't be that long because we have the previous step. So if you're wondering how we're able to do this one so quick, And we could do the student right there. We did that one yesterday though too, Blake. So maybe we should do this one and then check out yesterday where we did all the homework, and that one's on the homework one right there. We did it twice yesterday, actually, I think. So check out yesterday. This one we didn't do yesterday, so it's a really good one to end on. So what should you assume about p hat and q hat if you do not have p hat and q hat? I wouldn't like this as a test question, but what should you assume about p hat, q hat if you don't have them? If you don't get p hat and q hat, what would you assume? Well, so like you have no idea what the percentages are in the population. You don't know what percent conform. You don't know what percent not conform. It's like if I ask you what percent of UT students are blah, blah, blah. You say, what's a blah, blah, blah? And I say, it's a blah, blah, blah. So we don't even know what p hat and q hat are right now. You have no guesses. What's your best guess? What will be a good assumption? Think of a coin flip. What's a best guess? It doesn't say what p hat and q hat are. It doesn't say what p hat and q hat are. So what's a guess of them? They do. If you don't know what they are, what's the safest bet? Should you assume p hat is 1%? If you don't know, maybe you would assume they're what, 50-50? Kind of the naive, right? Or just like I don't know, why would I assume p hat's higher or q hat's higher? Let's just say they're both about the same. So without any knowledge, this actually creates the largest margin of error or largest sample size needed, since we'll be solving for that. So it's the most conservative route to go. And the only reason we're doing this is just without any knowledge of which one might be higher. We would just say, well, I don't know, about 50-50. So that will create a much larger sample size needed rather than things that are smaller. Thinking theoretically, yeah, I think so. And what do you see right here? That is the ME. And then what does 95% confidence tell us? That tells us the what we need. 95% confidence for the interval tells us the what. We just found the what right here with the David M. Lane. The 95% confidence tells us we need a certain what score. This is the what score right here. So I went to the second button. And on the second button, I entered 95 and went between. This is the Z score. So now we know the Z score for the 95% confidence interval. Z is equal to 1.96. And we're solving for the sample size we need from the margin of error formula right here. And guess what we do? Now, since we know all these values, we went through and checked out the last problem where we did the algebra to show how this works mathematically. Well, I mean, Dad's name's David. So we did all the algebra here previously, and they want a margin of error of 3%. So we're just using the exact same algebra from the previous problem to go in here and do P 0.5 times Q 0.5, because we assumed those. Z score of 1.96, square the quantity over the margin of error. And so that's just the algebra. It really comes down to knowing your notation. And we go right here, we put that Nash right there. And now we go 1.96 divided by 0.03, square the quantity, and times by 0.5, times by 0.5, and 1.0 or 1068. Make sure to round up, I think it says. It says round up. If you don't round up, just let me know, but it does say round up, and we did it correctly. So it really comes down to a knowing your notation problem. I like that we did these back to back. They're tougher problems, but it comes down to knowing your notation. And this one's a bit weird. I actually had an instructor ask me, it doesn't give p hat and q hat. What do we do? And I was like, well, if we don't know them, we should just assume the 50-50. What other guess would we have? So this comes down to knowing the notation, and then the margin of error is Z star times p hat times q hat over n. We know what the margin of error they want is, and all we're doing is solving for n. Yeah, so then you plug in the numbers right here, and we did the algebra. It's all about that
Notation, brother.
It's all about that notation. Does that make sense? Solve for n. Mm-hmm. So these are really tough. There's been like one of this on the test before, but I'm not the biggest fan of these because they're mainly algebra problems. They're not like statistical interpretation problems, which I enjoy more, which I think are better. But just plugging in the numbers and seeing how we use the margin of error right here. Ban this question. That's all right. It's a good notation problem. You got to know the margin of error right there, which is right here. You got to know your Z-score and how to find that. Your P hat Q. Yeah, it's easy. Once you know how to solve it, and then just make sure to round up. If you don't round up, I'll give you the points back. So when you see this right here, you have to round up. Since it's 0.11, you round up to 1000. 68, if you don't round up, it tells you you're wrong. Oh, it gave it to us now. They give a little margin of error. They might have added that into these questions, but it used to be wrong. Didn't know 50 and 50 were different. Am I? If let me know, Moira, right there, if you need a correction or not. Just let me know. Why does it get? It just says it's like seats at a restaurant. There's a question. I think, did we do that one already? The seats at a restaurant. Just sometimes it's like you need a certain amount, you'll round up. Like think about this. If I'm making cakes and it says make 1.3 cakes to feed everybody, I'm gonna round up. So there's instances in life when you think I need to make sure I have enough, and so you might round up even if you have like 0.3. Like order 1.3 pizzas would be order 2 pizzas because you can't order 1.3 and one would not be enough. So that's why you round up at certain times, like why you round up. Yeah, good questions. Pearson is bipolar, probably still. With that, class starting here in 10 minutes for the next class. Bye.